This session is entitled Security of Even-Mansour ciphers under key-dependent messages. It's a joint work between Kuya Fashim, Louisa Kati, and Tanya Bello, and Louisa will give the talk.
Okay, thank you for the introduction. So this paper was written with my advisor, Damien Bello, and Kuya Fashim from INS. It's about the current security of Even-Mansour ciphers. So KDM is for key-dependent message. It's a model that was properly defined by Vogel in the Shrimpton in 2003 in the paper titled Encryption Scheme Security in Prison with Key-Dependent Message. So in this paper, they consider the model where an encryption key can be encrypted by itself. So the question is it secure? Later in 2008, the paper Circular Encryption from Decision Diffie-Hellman gives some use cases, like disk encryption. When you want to encrypt your disk, there is some tool that will encrypt your disk at a low level. So if for different reasons the key ends up in the memory, it will be encrypted. So the question is it secure to have this kind of encryption? So this analysis is about Even-Mansour. So you already saw this scheme. It's a really basic scheme based on random permutations. So the Even-Mansour ciphers can have any number of rounds. Here you can see the R-round Even-Mansour. Here it's a scheme for different random permutation, different keys. But you can have other configuration like same key, different permutations, different keys, same permutation, and the more efficient, same key and same permutation. And sometimes you can have a master key that will be used to derive all these intermediate keys. So a lot of the work has been done on Even-Mansour. So the seminal paper by Even-Mansour showed that this one-round scheme is a strong pseudo-random permutation up to the birthday bound. Later, Shen and al. Showed that the two-round Even-Mansour is secure beyond the bound in the random permutation model in the configuration where P1 is equal to P2 and the intermediate keys are derivated from a master key. Later, the RK, the related key security was analyzed especially by Fashim and Proctor. In this model, we assume that the adversary can apply some offsets to all the keys, so we can change the key Ki to Ki XOR delta, so some constants. And they show that for the configuration where you have only a single key and a two-round Even-Mansour, we have CPA security, and that we need three-round Even-Mansour to have CCA security. And the last work done on Even-Mansour was done by Diane Al last year, and they show that five-round Even-Mansour are necessary and sufficient to have indifferentiability from an ideal cipher. So it seems that the KDM security remains to analyze. So here you have the KDM security model. So usually when you're doing indistinguishability proof, you have this adversary that is communicating with an oracle. And this oracle will either implement an ideal word where you have permutations that will enable encryption and another permutation to decryption. And you have the real world with your block cipher. So for us, it's the Even-Mansour cipher. But the KDM adversary is more powerful because he can encrypt constants, but he can also ask to encrypt some function depending on the key. So if he is playing in the ideal world, he will have this ciphertext, and if he is in the real world, he will have the Even-Mansour encryption. But for decryption, he can, in our model, in decryption, he can only decrypt constants because we didn't see any application of a model where the adversary can decrypt functions of the key. And an important thing is that it's forbidden for the adversary to decrypt a ciphertext that is a key-dependent encryption, because otherwise he will retrieve easily the key. Let's imagine that the adversary asks to encrypt the key, so it will ask to encrypt the identity function, so he will receive the corresponding ciphertext, and then he can just ask to decrypt this ciphertext to recover the key. It will be too easy. So now let's say that the adversary is allowed to ask any function phi from the set big phi, and we put no restriction on this set. So what the adversary can do is that he can use a function phi I that will set the 8th bit of k to 0, and he can also use the identity function to recover the key as follows. So the adversary will ask to encrypt the identity function, so the result will be here the encryption of the key, because the identity of key will be equal to key. And if the 8th bit of key is 0, we will have phi I of k that will be equal to k. So we will have the same encryption, and the adversary will know that this 8th bit is 0. Otherwise, he knows that it's a 1. And for each position, he can know which bit is it and recover easily the key. So that's why we need to put a first constraint on the set big phi. We need a set big phi that is claw-free. Claw-freeness means that we remove all this kind of function to have a set phi under which we can have security. So a set big phi is claw-free if for any couple of functions phi1 and phi2, the probability to have phi1 of k equal to phi of phi2 of k is high. So this kind of function has to be removed. So now, even if we take a set phi that is claw-free, we will see that we can have attacks on Even-Mansour one-hand. So here you can see the Even-Mansour one-hand with different keys, and as this permutation is actually public, the adversary can ask queries to this permutation. So what the adversary can do is the following. He can first extract key1 by asking the first function phi1 of k equal to key1. So here we will have a 0, and the output will be p of 0 to k2. And we can understand that if the adversary can compute p of 0, he can extract key2. And as he has a direct access to p, so he can do that. He will ask 0 to p, he will have p of 0, and then he will XOR this ciphertext to this value y1, and he will extract key2. Now he has key2, he can extract also key1. So the adversary can ask to encrypt the value 0, and the output will be this output. Then, as the adversary has already key2, he will XOR key2 to this ciphertext, and he will end up with the value z, that is p of key1. And once again, he has a direct access to this random permutation, and he can ask p minus of the value z and recover the key1. So to have a claw-free set is not enough, for at least for the one-round Even-Mansour. So here you have a table of the security proof we have in the paper. So here you have the number of rounds, the permutation, so the permutation can be equal or different, and the same for the key. You can have the same key or different keys. And here you have the constraints put on the set phi to obtain KLM security. So we didn't take into account functions that are dependent of the permutation phi I, because otherwise the adversary can easily perform some attacks. So what we can see is that even for the one-home Even-Mansour, we can have some KDM security if we exclude the functions that look like this. So the functions that are XOR with the function that are K1 XOR with some constants. And in the paper you can find all of this security proof, but we will study this blue line, so the security proof of the two-home Even-Mansour. And I will come back to this table later if we have time. So for the security proof, what we do is that we set some KDM rules, otherwise the adversary can easily attack. So the adversary cannot encrypt a decryption done by the oracle, and he cannot encrypt, yeah, I already said it. So he cannot perform encryption decryption such that he will come back to the identity. And to make this proof easier, we'll say that the adversary cannot do repeated queries, and the set phi has to be claw-free, and the function in the set big phi has to be independent of the internal permutations. So the idea is the following. So here we have the first game, so the real game, where the adversary can access the random permutation phi1 and phi2. Phi1 and phi2 are independent. And here the adversary can also ask to encrypt some function phi and to decrypt some constant c. And we want to know the advantage of an adversary that is trying to distinguish between these two worlds. And in this world we are in the ideal world, where we have pi e and pi d for encryption and decryption. So what we did is that we took Q and Q prime that are independent permutations, and the adversary cannot has access to this random permutation directly, at least. So to do the security proof, analyzing the advantage of an adversary trying to distinguish between these two worlds is too complicated. So we introduce this intermediate game, where we have this forgetful random oracle. This forgetful random oracle is just, it can be seen as a random generator. So each time you give him an input, it will give you an independent and random value, even if you ask twice the same value. So this forgetful random oracle was introduced to break the relationship between the input and the output to make the proof easier. So what we can see is that the advantage between the advantage of the adversary that is trying to distinguish between these two worlds are small, because the only difference is that here we have functions, and here we have permutations. So the hard job is between these two worlds. So what is the advantage of an adversary trying to distinguish between these two worlds? This is the two worlds you just showed, the two games you just saw. So here you have this adversary that have the direct access to pi, the permutation piece, right? And he can also ask encryption and decryption. And we can see that the introduction of this forgetful random oracle introduced many inconsistencies. And we will try to catch all these inconsistencies, all this collision that the adversary will try to trigger. So to do so, we first do two reduction due to the fact that the forgetful random oracle can be seen as a function, and it's not a permutation. So the first reduction is a reduction to an adversary that is playing in what we call the forgetful game. So the forgetful game is the following. We have an adversary that has access to an oracle, and this oracle either implements a permutation, a random permutation, or this forgetful random oracle. And what we can see is that as long as the adversary is not allowed to do repeated queries, and as long as the adversary cannot ask ask to the oracle a value in the forward query, receive the result and ask it in the backward direction, the adversary cannot distinguish easily the permutation from the forgetful random oracle, and it is reduced to an adversary that is trying to distinguish between a PRP and PRP. Another reduction is a reduction to the splitting, what we call the splitting game. In the splitting game, an adversary has access to two oracles, and these two oracles can be either the same permutation, or it can be a permutation and the forgetful random oracle. And we can see that if the adversary has this, more or less the same constraints, so if the adversary is not allowed to ask the same query to these two interfaces, and if he is not allowed to do these circular queries, its advantage is reduced to an advantage of an adversary trying to distinguish between a PRP and a PRF once again. So now there is many other collisions to catch. So the first family of collision is the collision between the forgetful random oracle and a permutation, a direct accessed permutation. So in the real world, we can see that if we have the same value here and here, so the input of P2 here and here, the result, the output will be the same, but it will not be the case in the second game. So how the adversary can treat this kind of collisions? He can ask, for example, to encrypt some function file, and he can ask the value x to the direct permutation P2, such that x will be equal to the input here. So the input here is phi1 of phi of k XOR k1 XOR k2. And we will have this equation, and the probability to trigger this collision is really small, because even if the adversary knows Q1, or if he succeeds to concept Q1, it is reduced to an adversary that will guess P2. We will have the same for the output, so the output will be P2 of x here, and the output here will be C XOR K3. Once again, if the adversary succeeds to trick such a collision, it is reduced to guess K3. And he can do this when he's asking forward query to P2. We'll have more or less the same behavior, because P2 plus and P2 minus share the same list. But he can also trick this collision if he asks a decryption query. And if he asks a query to the direct access to P1. So once again, here we will have a consistent behavior, and it will not be the case in the second game. And we will have also some equations, and what we can see is that this equation is reduced to guess some key. Okay, we will have the same with the backward query to P1 plus. Now we will take into account a second family of collision, is when we will have a collision between the forgetful random oracle and itself. Imagine that here the adversary succeeds to have the same input for different queries. We will have different output here, and here we will have consistent outputs. So the adversary can trigger this event by asking two different encryption queries. So if he asks to encrypt phi1 and phi2, we will have this input that will be equal for both phi1 and phi2, and when you analyze the equation, you can easily understand that if it happens, it means that phi1 is equal to phi2. Phi1 of k is equal to phi2. And as we said that phi1 has to be different from phi2, this kind of collision breaks claw-freeness. So if it happens, it's because the set phi is not claw-free, but we took a claw-free set, so it cannot happen. It can also trick this kind of collision by doing decryption queries, and if it's asked to decrypt two different messages, C1 and C2, and then we will have the same value here, it means that C1 is equal to C2, and once again it cannot happen because it's forbidden by our Canadian rules. Sorry. So the third family of collision.
I think you have only 2 minutes left.
Okay.
Go to all the cases.
Okay, thank you. So a third family of collision are the following: is when the forgetful random oracle collides with an internal permutation. Here we should have P1 minus, and the adversary can trick some inconsistencies by doing some queries. And we will have all these equations. And what we can see is that it can either it cannot happen with a high probability because it's used to be a key, or it breaks either the claw-freeness or either the Gaussian rules. So at the end, if the set phi is claw-free and all the functions are independent of pi, we have a security up to the birthday bound. Quickly, if we have an Even-Mansour scheme with the same permutation, we will have more collisions to take into account. So quickly to sum up, we just saw the Canadian security proof of the 200 Even-Mansour with different keys, different permutation. And actually, that's not the real security proof. It was just an easy way to present our security proof. What we did is that we built a general framework to analyze all this family of collisions with a two-stage adversary. So one part of the adversary has no access to the key, and the second part has access to the key. And with this framework, we believe that we can also analyze RK security. And we can also analyze other block ciphers, not only the Even-Mansour ciphers. And in the paper, you can also find the Canadian security proof for the ideal cipher, and all the table I just show you here.
Thank you very much. I'm afraid there is no time for questions, so we move on to the third talk in this session.
Okay.